Okay, worksheet 6 for ELC139, part 2. Determine the circuit response, then build. Determine the circuit response means analyze. Then build means to build. With a 10 millihenry inductance, a 0.47 microfarad capacitance in series with a 620 ohm resistor. Use a 5 volt source at 2320 hertz. And then your calculated values on one side, and then when you build, that will come from the analysis, SPICE. And then your measured values come from building the circuit and actually measuring. Okay, now when you build the circuit, you can get perfect resonance. You can adjust the frequency to where your voltage across your LC should be just about zero as read by your meter, and then you'll be perfectly at resonance, which this will be pretty close. I made another spreadsheet, and basically what I've done is I put in the capacitor value 0.47 e to the minus 6, which is 4.7 e to the minus 7 if you think about it, and 10 millihenries. So I got my capacitor and my inductor, and then I've got the formula down here that takes whatever value I put in A1 and A2, and it calculates what the resonant frequency is. So capacitors and inductors have a resonant frequency. And so I put in the equation. It's 1 divided by 2 pi times the square root of my L and my C, if you will, multiplied together. And that proves it. And then as you come across problems where I ask you that, all you got to do is change these values and the answer comes out. Spreadsheets are really handy for that. Later on we'll do some corner frequencies where we'll be comparing the capacitance to a resistor when the capacitive reactance is equal to a resistance, or the capacitive reactance is equal, or the inductive reactance is equal to a resistance. Those would be corner frequencies. So you could just sort of add this, and you could have an engineering spreadsheet to do a lot of the work where you can put in, it will give you Excel skills, or in this case LibreOffice Calc skills, and it will get you to where you've got right answers and you can solve problems and really make you look like a professional. Anyway, 2321.5 is the frequency, and I said use 2320. So I built the thing in SPICE, and when I built it in SPICE I used the frequency 2321.5, and here's my circuit: 10 millihenry, 0.47 micro, 620 ohms, 5 volt AC, dot AC analysis. If you don't remember how to get there, edit simulation command, and it's just AC analysis. Since we're just doing one point, it really doesn't matter what type, so just pick linear. But I think you could use the others. I don't know if they'll fail because there's only one point or not. Number of points is 1, and then you put in the same frequency twice. And that's the extent of the analysis we get. And when you get into deeper college level classes and you start looking at system frequency response for a system over a range of frequencies, that's really what this is for. So we're just using it for the one frequency we care to study in electronics. So I click OK, I click run, and there's my analysis. My frequency at node 1, which this is node 1, is 5, or my voltage is 5 angle 0, top line, minus 1.94 times 10 to the minus 20 is a 0. Then my voltage here between the capacitor and the inductor would read 5.14 at an angle of minus 13 degrees. And then my voltage on the other side of the capacitor between the capacitor and resistor is 4.99, which is essentially a 5, back at angle 0. So what you notice is the voltage here and the voltage here are identical. Okay, within reason. But they're effectively the same. This voltage is different, which means there's a voltage drop across the inductor and a voltage drop across the capacitor, and those voltage drops are 180 degrees out of phase, such that when you add them together they cancel out. So what I have here ends up here. And that's what I want you to see, and that's why I want you to build the circuit. I'm going to change up the video here since I can. I'm going to lower my resistance. I did some calculations the other day, and if I change my resistance to somewhere around 330, I think I can go as low as 220 and still safely build it. I don't remember. I think 330 should be okay. Okay, now I've got the same circuit. I've lowered my resistance. What you see now here is I have 5.46 volts or 5.47 volts at an angle of 23 degrees. So I'm going to see a little bit bigger shift. So I'm actually going to see more voltage at this point than my source is. And I'm at 15 milliamps. 15 milliamps times squared times 330 ohms. Does that exceed the power factor? If you check it, you can build it in lab and use these numbers if you'd like. I just want to do it so it's different. I've got my conversion spreadsheet open, so I'm going to use that to do my analysis. So I've got a 5 and a 0. Excuse me, 5 and a 0 is my first point, and then 5.47 is the magnitude, and my angle is minus 23.846. So I'm going to make that minus 24, and then this is 5 angle 0. So I'm just using the first 3 lines of my conversion spreadsheet to give me my node 1, and I can put in node 1, 2, and 3. Whoops. Node 1, 2, 3. Okay, so these are my voltages as read by a voltmeter at those 3 nodes. Now, you don't read the phase angle with a voltmeter. This is what they are in rectangular. So if I do the real and imaginary parts up here, I can add them up. So the first part is my voltage drop across my capacitor will be this number, the top line, minus the second line. So 5 minus 5 is 0. And 0 minus a negative 2.22 is positive 2.22. And I should have done that in the top one. Okay, so if I was to measure the voltage drop just across my inductor, it would read 2.22 volts. And if I was to read the voltage drop across my capacitor, it should also read the minus 2.22 volts. And I will get that by subtracting this number, which is row 15, from this number in row 14. So 5 minus 5 is still 0. Minus 2.22 minus 0 is now a minus 2.22, so I can change that. And what you see is I have identical numbers with the phase off by 180 degrees. And that's the neat thing about AC and reactive components. The inductor and the capacitor sort of cancel each other. And at the same time, the voltage level can be quite high. So if I lower my resistance, I will get even a bigger swing. So I can actually probably get 7 or 8 volts if I choose the right resistance from an analysis standpoint. I probably can't build it because I've got to have something to limit the current. But what you see is my voltage is in fact going up there at that point. And we probably can actually get it above 5. So let's minimize that. Close that. And just for fun, let's go down to about 50 ohms. Now you can't build a 50 ohm circuit. Okay, you can't do it. But the nice thing about all these simulations is you can. And what you notice here is I'm going from 5 to 15 volts here. So 5 angle 0, 15 angle 71. So I've got a pretty hefty swing. I've got like 10 volts. So I've got 10 volts or more across this. And I will have a correspondingly 10 volts drop across this, even though I'm only putting 5 volts in the system. Now my current is almost 100 milliamps. 100 milliamps through 50 ohms. You better have a power resistor if you're going to do that. Whatever that works out to be. So, but you get these tremendous swings right at the resonant frequency when they are put together. And I wanted to kind of illustrate that, and that was the whole purpose of the problem. Going back to the worksheet, you can use the 620. You can use 330 if you'd like to, but make a note on the worksheet that that's what you did. You can probably go as low as 220, but I want to see a calculation that it's safe to use 220. But it just means your VL and your VC get bigger. Your VL plus C should equal 0. And that's the main thing I want you to see in this. Okay, what capacitance value at 60 hertz would give a reactance around 800 ohms? Let's just make that automagic. Okay, so if I have a capacitance at 60 hertz, what give a reactance around 800? So I'm solving for C. So if I put in my reactance of 800 and my frequency of 60, that's XC and F, then I can come up with what C is. So C would be equal to 1 divided by, open parentheses, if you're using a calculator, this is probably where you're making a mistake, 2 times pi times frequency, which is C6. So that's times C6 times reactance, which is B6, and then close parentheses. So there's my frequency. 3.31 times 10 to the minus 6. So that's a very, very small frequency. That's almost DC. I mean, that's almost, that's a 3.31 microfarad capacitor. We're solving for capacitance. And if I had gone in and changed the problem and asked for 1500 ohms, now it solves it for you. You're down in capacitance. And you can go in your Excel and you can mark that and you can have it. At what frequency would a 3.5 microfarad capacitor and 0.03 millihenry have the same reactance value? Well, that is effectively what we saw for up here. We want the resonant frequency. So I need to put in different numbers. I've got a 3.5 micro. 3.5 micro is E minus 6. That's my capacitor, and my inductor is 0.3 milli. So 0.3 E minus 3 would be 3 milli, and that frequency should come out to about 4911. Now, what is the value at 4911? So if I put in a frequency of 4911, I can't work it backwards. So if I take either my inductive reactance or my capacitive reactance at 4912, so what is it? I didn't ask for that value, I just asked for what frequency. I didn't ask what the value of the reactance would be. So I'm just asking for the frequency, and that is the resonant frequency. That's what I'm asking for. Okay, I beat that one up. 17 to 20, given a series circuit, 400 ohms resistance, 500 ohms inductive reactance, 800 ohms of capacitive reactance, and 250 volts applied, what is the total impedance? What current would be expected? Multimeter read. You can't build this circuit, so this is all theoretical. What voltage drops would be expected? Okay, so I've got 400 ohms of resistance, 500 ohms of inductive reactance, 800 ohms of capacitive reactance. So I'm giving you inductive reactance and I'm giving you capacitive reactance. So I'm not giving you capacitive and inductive values. What you will see in this problem is my 400 ohms resistance goes out my positive x-axis, 500 ohms goes up, 800 ohms goes down. So this is essentially a 400 out, 300 down. So my impedance for this circuit in real and imaginary works out to be 400 out and minus 300 down. Okay, so I have an impedance of 400 minus 3i, which gives me a polar form of 500 and minus 36.87. So what current would be expected? I've got 250 volts applied and I've got 500 ohms of impedance. So my current should come out to be about a half an amp, and it will have an angle of positive 37 degrees. So I will have a current that is 0.5 at an angle of positive 37 for that problem right there. And I can bolden them, I guess. That's my current for this one. What voltage drops would you expect? Now I can take that individual current and I can go back in and I can multiply it by the resistance, the value of the inductive reactance, and the value of the capacitance. And you will see that you can get voltage values. So 0.5 times 400, and I really don't want that huge, so let's get back. 0.5 times 400 is 200 ohms, right? Or 200 volts. 0.5 times 500 ohms of inductive reactance will give you a 250 volt drop. And for your capacitance, 250, and for your capacitance you get a 400 volt drop. So if you were to measure this circuit and you put 250 volts in, you would drop 200 on the resistor, 250 on the inductor, 400 volts on the capacitor. But due to the angle and the fact that it's AC, if I converted all those numbers, took these numbers and the angles that come with it for the voltage, I converted them all to rectangular, added them up, I'd get my 250 angle 0. Anyway, that would put you into that kind of analysis is really important in fully understanding, is to go through and look at that. So take that current with the angle, multiply it times just your resistance, 400 at a 0 angle, write down that number with the angle. Same with the inductor. The inductor is 500 ohms at an angle of 90 times the current that you got, so you get a different voltage and a different angle. Capacitance is negative 90. Capacitive reactance is negative 90, 800, so you get a different voltage with a different angle. Take those three numbers, go to the conversion spreadsheet, put in the polar, get the rectangular back, and add them up. And they should add up to 250 angle 0, or 250 plus 0i, roughly. That is what you should do. And if you built that circuit and you came across that circuit, you can get those kind of readings. And you need to know that you can get you'll get a 400 volt drop across your capacitor, even though you're only putting 250 volts in the circuit. And it's supposed to happen. It's not magic. It's not a fault. It's not anything. That's just the way the circuit is. Anyway, I hope this helps you finish worksheet 6, and I appreciate your watching. Have a great day.